Hello folks, we come to the part 4 video of this exercise 1.1 and we are continuing with the problems which we were doing in the previous class. Here we are having the second problem which says that there is this relation R which is consisting of all these ordered pairs AB such that A is less than or equal to B squared. Now the question does give us in detail that this R, you are taking all the elements from the set of real numbers, and in the question they say that this particular relation is neither reflexive nor symmetric nor transitive. So as an idea we have learnt that whenever a certain relation is satisfying either of these conditions, we have to kind of give a proof, and suppose it is not satisfying, then we give a counter example. Because it is already hinted in the question that all the three are not getting obeyed, we are actually looking out for 3 counter examples for showing all these 3 properties, showing that these properties don't work. So let's find out the correct counter example and let's see how we are able to solve this problem. So first, right away we will check for reflexivity. Consider. Always generally for reflexivity we start with a consider some half-half. Okay, reflexivity, we know what is reflexivity. If this condition has to be obeyed, then every element may be 1 1, maybe 2 2, maybe minus 1 minus 1, maybe root 2, maybe something like 7 by 6, 7 by 6. This is the meaning of reflexivity. Every such element which is a real number, if of this form, should belong to R. If you are able to find even one such example which doesn't belong to R, then R is not reflexive. So our idea is to just find one element which doesn't obey this property, then we are done. So let's look out for fractions. Generally in inequality case, fractions work fine. So let's look out whether this is going to help us, otherwise we'll have to explore for some more examples. So let's check what happens to half-half. The moment it obeys this inequality, it belongs to R. If it doesn't obey the inequality, it doesn't belong to R. So let's see whether it is obeying or not. If you could check half is whether it is less than or equal to 1 by 4, which is half squared. See, A less than or equal to B square, whether it is half and 1 by 4. Half is not less than 1 by 4 because half is 0.5 and 1 by 4 is 0.25. It's not less. So that's not true, right? Because it is not true, this particular element cannot belong to R. Only if it satisfies this inequality, it can belong to R. This inequality is not getting satisfied, so we just at random we just checked it. Okay, we considered an element, we just checked it just to see if it is belonging or not. Sorry. And incidentally, it is not obeying the inequality. Like that, half-half is not belonging to R. Doesn't belong to R. Once it doesn't belong to R, what can we say? R is not reflexive. That's it. Yeah. So as we said, every time that a particular relation is not getting obeyed, we are just in a lookout for an element which doesn't belong, and generally fractions do wonders in such cases, because normal elements, they work fine, only fractions will create some kind of problems, right? You could also explore other fractions. We always try to keep it simple, because even when it has to be reproduced in the exam, such simple fractions becomes easy for us, to work and find out. Okay, symmetricness, same way. If AB belongs to, what is the meaning of symmetricness? That for any AB that is belonging to R, you've got to show that B comma A also belongs to R. So here probably you should find an element that's belonging to R, but it should not, the reverse element will not belong. That's what we are going to search. So let's see. Let's start with a normal element and let's see if it works fine. Otherwise, as I said, we can use some other example. 1 comma 2 belonging to R. Does it belong to R? Let's check. Since 1 is less than or equal to 2 squared, which is 4. 1 is less than 4. So that is why it is belonging to R. That's what we try to reason. But look at 2 1. Yeah, 2 1. Here 2, whether it is less than or equal to 1 squared. 1 squared is 1, 2 is less than 1, that's not true. Therefore 2 comma 1 cannot belong to R, that's not possible. Therefore R is not symmetric. Yeah, intuitively we knew it, that it's not going to be symmetric. Only thing we were searching out for an example, right? Next we can search for transitivity. Let's look at this. Let what? 2, 1. Sorry. Such kind of strange things with minuses and 1. Generally this 1, though it acts as a buffer and helps us, so that is why we try to get the 1s and we try to get some minuses into the picture, so that this transitivity thing we are able to show. These are, as I said, in this generally we'll use fractions. In this we'll generally pull in either some minuses or some 1s, so that you are able to show this. Let's see if it is working. As I said, if it doesn't, we will explore for other examples. Whether it is belonging to R, first let's check. If it's not belonging to R, at the very outset we have to change the example itself. Since 2 is less than or equal to, no, that's what I said. See, 2, 1, 2 is less than or equal to 1 will not work. So let's have it altered. Let's have it as 2 minus 2 and minus 2, 1. And let's check how this is coming. 2 is less than or equal to minus 2 squared, which is 4. That's true. And minus 2 is less than or equal to 1 squared, which is 1. This is okay. See those elements, you have to be intelligently meddling with those elements. So these are belonging. Why? Because these two inequalities, 2 is less than or equal to minus 2 squared and minus 2 is less than or equal to 1 squared. Like that they are belonging to R. Therefore, we have to consider 2, 1. This is pathetic. We have seen it here, right? 2, 1. But 2 is not equal to 1 squared, not less than or equal to 1 squared. Therefore, 2, 1 will not belong to R. So, starting with this, we have reached here. Starting with 2, minus 2, one element, minus 2, 1 belonging to R. If it was transitive, 2, 1 should belong to R, but that doesn't happen, doesn't belong to R. Therefore, R is not transitive. So that's how we show. Actually, showing that something is actually more challenging as compared to something which it's easy. You just have to show like kind of proof you are getting it. But in the exam, the right example should strike you. Or sometimes it so happens that the right example just wouldn't come, and you'll waste so much time in the exam. So you should have your own technique of grasping these examples, and without much time delay, you should be able to reproduce it in the exam, if at all it comes. That's about it. Then we are taking the question number 3. It's a pretty good question. It says that your relation is defined on the set 1, 2, 3, 4, 5, 6, and the relation is defined of, it is made up of all the ordered pairs such that B is A plus 1. That means B equal to A plus 1. So what we will do is, because it's a small set, earlier set was entire real number. You cannot even think of listing the R, it will be like so voluminous. But here, because it's a small set defined only from 1 to 6, it's worth listing the R. So once you have listed the R, for you to check reflexivity, symmetric, transitive is much easy. So maybe we'll try it that way. So we'll do one thing, let xp1, xp2, all this we will list and find out. X is 3, X is 4, X is 5, X is 6. These are things which you are allowed to take, and let's take their corresponding y's. Y is 1 plus 1, which is 2. Y is 2 plus 1, which is 3. Y is 3 plus 1, which is 4. Y is 4 plus 1, which is 5. Y is 5 plus 1, which is 6. Y is 6 plus 1, which is 7, right? This is how the relation works. This is how the condition works. Now let's see what all elements you can include. Now the thing is, you cannot include all the elements. You can include only those elements which belong to the set. Once any of the element, if they go out of the set, you cannot include them, right? So here you can have the element 1, 2 can belong, 2, 3 can belong, 2, 3, then 3, 4 does belong, then 4, 5 does belong, 5, 6 does belong, but 6, 7 will not belong. Why? Because the 7 is going out, right? So these many elements are there in our set R. Now we have to check. Now this reflexivity and all that is pretty trivial. See, let's check reflexivity. Reflexivity. 1 1 does it belong? Not there. 2 2 not there. 3 3 not there. 4 4 not there. 5 5 not there. 6 6 not there. So none of the elements are there. It's not reflexive. Okay, if it has to be reflexive, we have to have those elements. So we can write, since any element you can write, but somehow 1 seems to be good, doesn't belong to R, therefore R is not reflexive, as easy as that. Then symmetricness. Yeah, 1 2 is belonging where the 2 1 is belonging, not there. Simple, right? Here 1 2 belongs to R, but 2 1 doesn't belong to R, so R is not symmetric. R is not symmetric, right? Then we'll check for transitivity also. Yeah, you know, this overlapping element, yeah, you can get it everywhere. Yeah, we'll take these two elements. Now 1 2 and 2 3 belongs to R, but again 1 3 doesn't belong to R. That's how we check transitivity, right? This common element you skip, and those two uncommons or those two extreme elements we take, right? So 1 3 doesn't belong to R, therefore R is not transitive. Got it? So it's only that much. We are going to like explore how we can do these kind of problems. That's all in this video, with new problems in the new video. Thank you.